Stand at the corner of 4th and Vine Streets in Cincinnati, Ohio, and look up at a 210-foot tower that should not exist. In 1903, when this 16-story structure first pierced the skyline, every engineer in America knew concrete buildings couldn't rise beyond 6 stories. The material would crumble. The weight would crush itself. The structure would collapse, killing everyone inside. Yet Melville E. Ingalls spent 2 years fighting city officials for a building permit, insisting his vision would stand. He wasn't proposing steel beams clad in masonry like every other skyscraper in the country. He wanted to pour liquid stone from the ground to the roof, creating a monolithic giant that defied every accepted principle of construction. The city said no. The engineers said impossible. But Ingalls knew something they didn't. A secret hidden in twisted metal that would change construction forever. To understand how the Ingalls building survived when it should have failed, you have to see what really happened in those 8 months of construction and what one California inventor discovered about the marriage of concrete and steel. The year 1903 belonged to steel. Across America, skyscrapers rose on frameworks of riveted iron beams, their skeletons visible against city skylines before masons arrived to wrap them in brick and stone. This was the proven method, the safe method. Steel carried the load while concrete served merely as fireproofing, poured between beams to protect them from the flames that had consumed so many wooden structures in the previous century. The tallest buildings in New York, Chicago, and Philadelphia all followed this formula. When architects spoke of concrete in structural terms, they meant foundations and basements, the invisible parts buried beneath streets where failure wouldn't kill pedestrians. The material had a reputation problem. It cracked unpredictably. It weakened under tension. It couldn't span distances or support the concentrated loads that tall buildings demanded. Every structural engineer learned these limitations as fundamental truth. But in San Francisco, a 59-year-old English immigrant named Ernest Leslie Ransom had been conducting quiet experiments that challenged conventional wisdom. Since arriving in America in 1870, Ransom had watched concrete fail in precisely the ways engineers predicted. He'd seen slabs crack under modest loads, beams sag and fracture, floors collapse during construction. The material possessed tremendous compressive strength. It could bear enormous weight pressing down on it. But the moment tension entered the equation, pulling rather than pushing, concrete failed catastrophically. Ransom understood that every beam spanning a gap experiences compression on its top surface and tension on its bottom. Concrete alone would always crack at the tension point. The solution seemed obvious. Embed something strong in tension within the concrete itself. Iron bars had been tried before with mixed results. The bars slipped within the concrete matrix, failing to transfer loads effectively. The bond between materials wasn't strong enough. On March 11, 1884, Ransom received U.S. Patent 305,226 for a deceptively simple innovation. He'd been testing iron bars with various surface treatments when he realized that square bars, when cold twisted along their length, created spiral ridges that locked mechanically into concrete. The twist transformed a smooth interface into a threaded connection. As concrete cured around these twisted bars, it gripped the spiral surfaces with tremendous force. When tension pulled on the reinforcing bars, the concrete couldn't release them. The two materials became genuinely composite, each compensating for the other's weakness. Concrete provided compressive strength and protected steel from fire and corrosion. Steel provided tensile strength and prevented concrete from cracking. Together, they created something stronger than either material alone. Ransom called it reinforced concrete, though composite construction might have been more accurate. For nearly 2 decades, Ransom built steadily larger structures to prove his system. In 1889, he constructed the Leland Stanford Junior Museum in Palo Alto using reinforced concrete, a building that survived the 1906 San Francisco earthquake, while unreinforced masonry structures around it collapsed into rubble. He built factories, warehouses, and bridges, each project pushing the limits slightly further. He published technical papers explaining his calculations and construction methods. Slowly, a handful of progressive engineers began to pay attention. The material offered advantages beyond structural performance. A reinforced concrete building required no structural steel, eliminating dependence on steel mills and their fluctuating prices. It provided superior fire resistance, crucial in an era when urban fires regularly consumed entire districts. Construction could proceed with less skilled labor since pouring concrete into forms required different expertise than riveting steel beams hundreds of feet in the air. The economics appealed to developers looking to build quickly and cheaply. Melville Ezra Ingalls saw these possibilities clearly. A railroad executive and real estate developer, Ingalls had watched Cincinnati's downtown core expand with steel frame buildings that required expensive fireproofing and lengthy construction schedules. He'd read Ransom's technical papers and visited several reinforced concrete structures in California. The system worked at modest scales. Could it rise to skyscraper height? No one had tried. The highest reinforced concrete building in 1901 stood just 6 stories tall. Engineers cited specific reasons for this ceiling. The cumulative weight of concrete floors would crush lower columns. Wind loads would crack the monolithic structure. The building would be too heavy for typical urban soils. Ingalls believed these objections could be overcome with proper design. In 1901, he approached the architectural firm of Elsner Anderson with an audacious proposal: design a 16-story office building constructed entirely of reinforced concrete, using Ransom's twisted bar system. Alfred Oscar Elsner accepted the challenge. Born in Cincinnati in 1862, Elsner had studied at the Ohio Mechanics Institute and later at MIT, training in both art and engineering. He understood structural systems as deeply as aesthetic principles. For the Ingalls building, Elsner designed a pure frame structure where every column, beam, floor slab, and foundation wall would be cast in place as a continuous, monolithic unit. The building would measure 50 feet along 4th Street and 100 feet along Vine Street, rising to 210 feet above grade. Each floor would act as a rigid diaphragm, tying the structure together and distributing wind loads across all vertical elements. The design called for columns measuring 18 by 24 inches at upper floors, expanding to massive sections at ground level to support the accumulated weight of 15 floors above. The entire framework would be poured in sections, with each floor tied to the columns and each column keyed into footings driven deep into Cincinnati's clay soils. The design was sound on paper. Convincing city officials proved far more difficult. Cincinnati's building department had no provisions for evaluating reinforced concrete structures. Existing codes addressed steel frame construction and load-bearing masonry. They specified nothing about twisted reinforcing bars, monolithic pours, or composite structural action. The building inspector's primary concern was public safety. If this experimental building collapsed during construction or occupancy, the death toll could be catastrophic. For 2 years, Ingalls lobbied, arguing, explaining, and providing calculations. He brought in structural engineers to review Elsner's plans. He cited Ransom's successful projects. He offered to have the completed structure tested beyond normal requirements. The building department remained skeptical. Concrete buildings were 6 stories tall. This one proposed 16. The leap seemed reckless. What finally convinced officials remains partially obscured by history, though records suggest a combination of economic pressure and structural guarantees. Cincinnati's business community wanted modern office space. Ingalls committed to rigorous inspections during construction. Most crucially, preliminary cost estimates revealed significant savings. The contract price came in around $500,000, roughly 20% less than a comparable steel frame structure would have cost. When Elsner demonstrated that steel framing would have required approximately $575,000 for the same building, the economic argument became compelling. In early 1902, the building permit was finally issued. Construction could begin. The site preparation commenced in August 1902. Workers excavated to bedrock, removing tons of earth and unsuitable soil. The foundation design called for massive concrete footings beneath each column, distributing loads across sufficient area to prevent settling. These footings were poured first, using plain concrete without reinforcement since they worked entirely in compression, bearing weight into the earth. As footings cured, carpenters began constructing formwork, the temporary wooden molds that would shape liquid concrete into columns and beams. This formwork represented one of the project's great challenges. Thomas Edison would note just a year later in 1903 that concrete construction absurdly required erecting 2 wooden walls to get 1 concrete wall, an observation painfully accurate for the Ingalls building. Every column required a 4-sided wooden box built precisely to dimension. Every beam needed a horizontal form suspended at the exact height. Every floor slab demanded a complete wooden deck supported by temporary posts. The volume of lumber and carpentry labor exceeded anything required for steel frame construction. The concrete itself came from local suppliers who mixed Portland cement with sand, gravel, and water in proportions specified by Elsner. The mixture had to be fluid enough to pour into forms and flow around reinforcing bars, yet stiff enough to develop strength as it cured. Too much water made for easy pouring but weak concrete. Too little created a stiff mix that wouldn't consolidate properly, leaving voids around reinforcement. The work proceeded floor by floor. Reinforcing bars were positioned in forms according to engineering drawings. Bars twisted to Ransom's specification, creating those crucial spiral ridges. In beams, bars ran longitudinally near the bottom surface where tension would occur. In floor slabs, bars formed grids to resist bending in multiple directions. Vertical bars and columns extended upward, waiting to be tied into the bars of the next floor's columns, creating continuous steel threads running from foundation to roof. Once reinforcement was positioned and formwork inspected, the concrete arrived. Workers shoveled the wet mixture into forms, using tools to work it around reinforcing bars and eliminate air pockets. This was brutal physical labor. Concrete arrived in wheelbarrows and buckets, hauled by hand to wherever it was needed. There were no mechanical pumps or mixing trucks in 1903. Every cubic yard of concrete moved by human muscle. The pouring had to proceed in carefully planned sequences. A column couldn't be poured partially and then resumed days later. The joint between old and new concrete would create a weak plane. Each element needed to be poured completely in one continuous operation. 4 large floor slabs. This meant crews working through the night, feeding concrete into forms until the entire surface was complete. The structure rose slowly, floor by floor, through fall and winter. After concrete was poured, it needed time to cure, to develop its characteristic strength through chemical reactions between cement and water. Engineers knew concrete gained most of its strength in the first 28 days, though it continued hardening for months afterward. This meant formwork couldn't be stripped too early. The concrete had to cure sufficiently to support its own weight plus the weight of workers and materials for the next floor. Timing these operations required judgment and experience. Strip forms too early and green concrete could crack or sag. Wait too long and construction slowed to an expensive crawl. The construction crew walked a careful line, testing concrete strength by eye and feel, removing forms when the material seemed ready. Throughout construction, skeptics waited for failure. Engineers from rival firms visited the site, examining the rising structure for signs of distress. Newspapers reported on progress, noting the unusual building method. Some predicted collapse. Others suggested cracks would appear as the structure gained height and weight. The concrete, however, performed exactly as Elsner and Ransom had calculated. The monolithic structure distributed loads efficiently. The twisted reinforcing bars prevented cracking at tension points. The rigid floor slabs tied columns together, preventing buckling. As the building rose past 6 stories, then 8, then 10, doubt gradually transformed into cautious acceptance. This might actually work. The human cost of construction remains less documented than the technical achievement, though scattered records suggest the work environment was dangerous in ways both familiar and unique to concrete construction. Workers handled materials that could burn skin. Wet concrete is caustic, attacking exposed flesh. They worked on temporary platforms high above the street, often in winter conditions. The formwork was only as safe as the carpentry that built it, and structural failures during construction were common enough across the industry that insurance companies calculated expected casualties for every major project. A skyscraper construction firm would later admit that during the 1920s, 1 worker died for every 33 hours of employed time on tall buildings. Whether the Ingalls building's concrete construction proved safer or more dangerous than steel frame work isn't entirely clear from surviving documents, though the absence of documented fatalities during construction suggests either good fortune or careful management. By spring 1903, the structure was complete. The formwork came down, revealing the gray concrete surfaces beneath. The building stood. It didn't crack. It didn't settle excessively. It didn't collapse. Melville Ingalls had been right. Alfred Elsner's calculations held true. Ernest Ransom's twisted bar system worked at skyscraper scale. The 16-story Ingalls building became the world's first reinforced concrete high-rise, proving that the material could compete with steel for tall building construction. The exterior was clad in white marble at the lower 3 floors, with brick and terracotta above, following Beaux-Arts architectural traditions. But beneath that decorative skin, the structure was pure concrete and steel working in composite action, a genuine innovation in structural engineering. The building opened for occupancy in May 1903. Tenants moved into office spaces that were quieter than steel frame buildings, which transmitted noise and vibration through their rigid frameworks. The concrete structure provided excellent fire resistance. Maintenance costs proved lower than steel buildings, which required periodic painting and inspection of riveted connections. Insurance companies, initially wary, gradually accepted reinforced concrete as equally safe. Other developers took notice. If concrete could rise to 16 stories in Cincinnati, why not 20 stories or 30? The technical barrier had been broken. Ernest Ransom never saw the full flowering of his invention. He continued working into his 70s, building pioneering concrete structures across America, but died in 1917 before reinforced concrete truly dominated tall building construction. That dominance came later, in the 1920s and beyond, when engineers refined the system and developed comprehensive theories of reinforced concrete behavior. What Ransom, Elsner, and Ingalls achieved in 1903 was the crucial proof of concept, the first demonstration that reinforced concrete could rise to respectable height, support real loads, and remain standing year after year. The Ingalls building still stands today at 4th and Vine, now operating as a courtyard by Marriott Hotel after a renovation completed in 2020. The concrete poured in 1902 and 1903 continues bearing its intended loads, more than 120 years after construction. Modern engineers who have examined the structure express professional respect for the design and execution. The reinforcing bars, protected from corrosion by concrete cover, remain largely intact. The columns and beams show the normal wear of a century, but no structural distress. The building has survived not just gravity loads, but also the thermal cycling of 120 summers and winters, seismic tremors, windstorms, and the cumulative vibrations of urban life. This longevity raises questions about our current approach to construction. Modern concrete buildings are typically designed for 50 to 100-year service lives, with the expectation that reinforcing steel will eventually corrode and require structural intervention. Yet the Ingalls building, designed with 1903 knowledge and materials, has lasted well beyond such projections. Partly this reflects conservative design. Elsner's calculations included substantial safety margins because the structural behavior was incompletely understood. The building is likely over-designed by modern standards, with more concrete and reinforcement than strictly necessary. But it also demonstrates that well-executed reinforced concrete, when properly detailed and protected, can achieve remarkable durability. The broader legacy extends beyond any single building. The Ingalls building proved that concrete could compete with steel in the vertical dimension, opening new possibilities for architects and engineers. Through the 20th century, reinforced concrete enabled structures that would have been impossible in steel. Thin shell roofs spanning vast spaces, cantilevered balconies extending from facades, sculptural forms following curves and complex geometries. Architects like Frank Lloyd Wright, Le Corbusier, and Oscar Niemeyer exploited concrete's plastic quality, its ability to be cast into almost any shape. Engineers like Pier Luigi Nervi and Felix Candela pushed the structural possibilities, creating concrete structures of breathtaking elegance and efficiency. Today, reinforced concrete is so commonplace that we rarely consider its revolutionary nature. Nearly every building, bridge, and infrastructure project uses the material. Global concrete production exceeds 30 billion tons annually. The fundamental system, steel bars embedded in concrete, working in composite action, remains essentially unchanged from Ransom's 1884 patent. Modern variations include higher strength materials, better understanding of structural behavior, and improved construction techniques, but the core principle persists. Concrete resists compression. Steel resists tension. Together, they create a structural material that has literally reshaped the built environment. Yet this ubiquity brings environmental costs that Ransom, Elsner, and Ingalls never considered. Cement production, the crucial ingredient in concrete, generates roughly 8% of global carbon dioxide emissions. The industry's contribution to climate change is enormous. As we confront this reality, engineers and materials scientists are developing alternatives: geopolymer cements, carbon-sequestering concrete mixes, structural systems that use less material more efficiently. The challenge is finding solutions that preserve reinforced concrete's advantages while eliminating its environmental damage. This may require innovations as fundamental as the twisted bar was in 1884. Standing before the Ingalls building today, you're looking at the physical evidence of a moment when conventional wisdom was overturned by careful engineering and calculated risk. Melville Ingalls fought for 2 years to build something everyone said was impossible. Alfred Elsner designed a structure that pushed beyond established limits. Ernest Ransom developed a material system that would transform construction globally. They succeeded because they understood structural principles deeply enough to challenge accepted constraints. They built not just a building, but proof that progress requires willingness to test new approaches against real-world conditions. The question now is what constraints we're accepting as unchangeable when they're actually just limitations waiting to be overcome. In 1901, concrete buildings couldn't rise beyond 6 stories, except they could, and did, once someone tried with proper engineering. What are we assuming can't be done with current materials, current methods, current thinking? How many innovations remain locked behind assumptions that have never been properly tested? The Ingalls building stands as a permanent reminder that impossible is often just unexplored, that the limits we accept are frequently the limits we create. What do you see when you look at a structure everyone said couldn't exist? Share your thoughts below.